So FM1 from 2024 then, let's do it. So we have some speeds before and we have a speed afterwards. Kinetic energy before is just half mv squared plus half mv squared where you use the two speeds. We need to work out the speeds first, so it's 3 squared plus 1 squared. You could put a minus here, but it's obviously not going to make a difference. Same thing for over here. And then of course it's just a half mv where m's are 3 and 2 respectively, so it's just half mv squared plus half mv squared for their respective speeds and weights, and masses I should say, and we end up with this. The impulse is mv minus mu, so that's just going to be, again, this is for A. Now, you might not know which way round it is to do it, but you only know the initial and the before and the after speeds for A, so you may as well just do it for A, especially since working out the afterwards speed for B is part C. So you know that this is going to be mv minus mu with respect to A. Any amount of logic will tell you that. So okay, we obviously just need to work with this, and we end up with that there, which will be our answer. And then the velocity after the collision, well, we can now just use conservation of momentum, m times the initial speed for the first particle, plus m times the initial speed for the second, equals m, and so on. And I've just called the speed of B afterwards AB. And now, of course, we can just, I mean, you could have just written an equation using the top row and the bottom row separately, or you can just collect the vectors up like this, and divide everything by 2, and you end up with your answer there. So that's question 1 done, nice and straightforward. If tan alpha is 3/4, imagine a triangle with opposite side 3, adjacent 4. That's the 3-4-5 triangle. So sine is 3/5 and cos is 4/5. So yeah, you could have just inverse tan this and then got the decimal answer and then put in cos and sine of those, but I mean, you lose a lot of respect from me if you do that. We've got an inclined plane, and we've got a speed of root 2ag going up this way. So that's the speed that it's projected at. Obviously, we've got mg coming down, and we've got mg cos theta here, mg sine theta here. Those two things are very easy for me to write down because I know sine theta is 3/5. So this is just 3/5 mg, and this one here is 4/5 mg. So that's fine. That means this is also 4/5 mg, which means the force, the maximal frictional force, is 4/5 mg times 1/7 in this direction. This direction, of course, because that's going this way. I've incidentally answered question A there, so that's fine. I guess we've done that. We're currently trying to work out D. D is the distance that it travels in this time. So firstly, we're obviously going to use work energy principle because it says so. So the amount of kinetic energy lost is going to be all of this because it goes up to somewhere where it's at rest. So I guess you could say it's a half mv squared minus a half m0 squared, but I don't need to, right? We're just going to lose all of this kinetic energy, this being its initial speed. Gravitational energy, now it travels up this far D, but that doesn't mean it travels up D, right? Upwards it's traveling this far, and it's the upwards distance that we need for this gravitational potential energy that we gain. But of course, using, what is this, corresponding angles, that's also theta, which means this is d sine theta, which is again 3/5 d. So the upwards distance traveled is 3/5 d, so this is just going to be mgh, where h is 3/5 d. And again, we can define kind of the base here to be 0 height, so we don't need to get rid of anything there. We're just going to gain that much gravitational potential energy. Work done is the distance traveled times by the resistance. The resistance, as we said, was 4 mg over 35 times by the distance. It actually is this distance because it does travel that far along the surface. So that is actually the right thing there. And then we'll just use, I always do it like this. I don't know whether I'm stupid for doing it. This is just how I've always done it. Loss minus gain equals work done. So it's going to be this minus this equals that is how I'd always set this out. And it works out quite well. I mean, the 2 here cancel, so you just get this. Apologies for writing these letters in a completely anarchistic order. But you can, of course, cancel the mg anyway. And then you add that in, and then you can divide, and you get d as 7/5 A. Assuming our resistance to be, oh no, we've already done that. Cool. Oh, is that the whole question? Fantastic. Good. The whole thing is done. Question number 3. So we have a thing that's a weight of that, or mass, I should say, of 1,000. Resistance 900. Force is power over velocity over here. Now the thing is that velocity should be in meters per second for our units to make sense. So we need to convert this to meters per second at some point, and I think I'll do that pretty soon. I also said because it's constant speed, that means the acceleration is 0, which means this is equal to that. But again, I can't really do this until I have v in meters per second. So it's going to be 72 times 1,000 to get it to meters, divided by 60, divided by 60 to get it to minutes, and then to seconds. And that equals that. Put that in there and we get this, but that's in wattages or watts. So we times or divide by 1,000 to get P is 18,000 watts, we'll just say. Okay, now we're going up a slope with alpha being 2/49ths. So we've got mg coming straight down, of course, which is 1000 g. And likewise, this is going to be mg cos theta, this is going to be mg sine theta. This is the only one that I care about because this has the frictiony bit in it, I guess, so we don't need to do the whole this and then mu this or anything like that. So anyway, we have an acceleration that's just given by a, I think. We're traveling at 10 meters per second. So when v is 10, this minus this is equal to 1000 a. I mean, it's always equal to 1000 a, I guess, but specifically what they want us to find a when v is 10. So we'll put v as 10 in, and we'll just type that into a calculator, and we'll get a as this, and that is that done. Later, we're working at 30,000 kilowatt hours, so I've put that there again, just like before. But this time we're traveling at speed u, big U, and we are going at a constant speed. So therefore, this equals this plus this. The forces are just all balanced if it's a constant speed. Times everything by u, I just typed that into a calculator to get this, divide by 20, put that into a calculator as well, and you end up with this. U is obviously 30 since it can't be minus 50. And that's that question done as well. This is the setup for this question then. A particle of mass 2m going 3u in this direction hits a stationary particle here of mass m, and later I just said they were going at v1 and v2 after the collision. So let's just set up the things that we usually set up. So conservation of momentum says 3u times 2m plus 0 times m is equal to 2m times this plus m times that. We've got E is equal to separation over approach. I tidied that up a bit, cancelled the m's. E is equal to separation, which is this minus this, over approach, which is obviously just 3u because this one's not going anywhere, times that across. And now I think we're looking for speed of B. It doesn't actually really matter because in these kind of questions, you basically always want to get both of these in terms of the original constants. But if we're looking for V2, since that's the question they've asked us, I think I doubled this equation here, and then I can add this one to get rid of V1, I guess. And then, of course, you can divide and you get what they wanted. But now, like I said, I'm just going to substitute that into this equation here. And then I can find V1 is given by that thing there, which I just rearranged to be that. And the reason that's very helpful is because immediately afterwards it says, show there's a second collision when there's a wall over here and this thing hits the wall. Now, if this thing hits the wall and comes back, there's going to be a second collision if this thing is positive, right? And as soon as you look at this thing, now that we have it, we know this is positive because U is positive and E is less than 1. So this bracket is also positive. So therefore, this thing is traveling to the right, this thing is traveling to the left. So there's going to be another collision. So pretty trivial once you've worked out this one as well. So just a good rule of thumb is even if they only ask you for one, just work out both before you get to the rest of the question. What's happening next is the coefficient on this wall is a half. So the outward speed after this one hits it is just a half of this, which is that. And in simplified form, the magnitude of the impulse, so that's just mv minus mu again. So that's m times v minus m times u. U is going the different direction, so one of these has to be a negative as opposed to the other one. It doesn't matter which you do, because even if you did it the other way around, you just end up with a minus here, and the magnitude is just a positive number, right? So we would just leave it as this anyway. But as long as you have one of those minus one and plus, because they're going in opposite directions, you should be fine. Then the loss of kinetic energy of B, well, again, pretty straightforward, just a half mv squared minus a half mu squared. I've factorized out the half m already. This is, what is this, u squared and this v squared, I guess. Again, even if you've got those the other way around, it doesn't really matter because you would just go with a negative at the end anyway. Square these things out, of course, they come together pretty easily and you end up with that as well. Good, we've got a string hanging from the ceiling, as we often do. It's already stretched length A, right? So the A to E this is 3A and the natural length is 2A. So it's already stretched length A there already. Now, I'm going to say that when it's projected downwards, it's going to stretch another D. So the total stretch when it's at the bottom is going to be D plus A. Is going to be the total stretch. And now we're just going to do, again, energy principles here. So kinetic energy lost. Well, it initially has this much, half m, this thing squared, kinetic energy. And at the end, it's going to have 0 because it's going to have speed 0 here. So that's all the energy lost. That simplifies to that, I think. And then we're going to talk about gravitational energy lost. Well, it's going to drop down a distance d. So that's just going to be mgd, defining kind of this to be the 0. You don't need the thing there. You could go from up here, but it's kind of unnecessary. It just goes down d, so we're going to lose this much gravitational potential energy. And then in terms of elastic energy, kind of the tricky one, I guess. Elastic energy, of course, is lambda x squared over 2l. So initially, it's going to have an extension of a, as we already discussed. So that's why I've taken away a squared there. And at the end, it's going to have a stretch of a plus d. So that's going to be a plus d all squared. So I could have written this out as two terms, but I couldn't be bothered. So it could be, you could consider it as lambda this thing squared over 2l minus lambda this thing squared over 2l, but I just grouped them together because this is going to be the gain, right? This is how much it has at the end to take away how much it has at the start. I couldn't resist an opportunity to do difference of two squares here. D plus a minus a is just d. D plus a is d plus 2a. So that simplifies that when you cancel these twos as well. And now, of course, the gains must be equal to the losses because there's no work done here. So you just end up with this plus this equals this. MGs cancel as they so often do. This looks like it's not going to go very well, but then the two ADs cancel in a rather satisfying way. And then, of course, you can just root because A and D are both positive numbers, and we end up with that there. So that's the distance D that it travels down, and it says find the elastic energy and store in the string when it's at the rest. So that's just when it's stretched A plus D, which is A plus 2A, sorry, which is A plus 3 over 2A, which is 5 over 2A. And again, this is just lambda x squared over 2L, because that's what they're asking us to do, the energy stored at the bottom. This is 25 over 4. These twos cancel. That becomes an H there, and the A's cancel as well, and you end up with that there as our answer. Question number 6, kind of a weird question here. I got a tiny bit confused for a second because I initially drew it like this because I read vertical wall. I was like, oh, vertical. But then you realize this picture makes no sense because this vector has to be traveling in this direction, but it just can't be because that doesn't make any sense for these numbers. So then maybe you draw it horizontally, but this also doesn't make any sense because, oh no, this does make some sense, no? 4 minus 1 is this way, and then 1, 3 is this way. This makes sense initially, but then you realize, of course, that the horizontal component is not maintained. 4 and then 1 is just not how that works. It should be 4 and then 4, or 1 then 1. So this doesn't work either. So instead, you're forced to draw like this. And when it says vertical wall, it doesn't mean vertical like this necessarily. It just means that the particle hits it, and it's in its own sort of plane of existence. It's hitting a wall that's not going to, it's not going to scoop up. It's not like a ramp to itself. It's not going to scoop up, or the wall isn't bent towards it. It's just a vertical wall. Just like when you see a wall in your house, you think it's a vertical wall, but you're not actually asking whether it's going north, right? It's just a vertical wall. It's parallel to it's perpendicular to the floor is what you mean by vertical. So this could be a vertical wall as long as the particle, of course, is traveling along an imaginary floor that is perpendicular to how this wall is rising out of it. That's all it's really saying. Anyway, that's probably everyone. I think I'm just done. Everyone, I think, understood that immediately. I just got into a bit of a mess with it. Anyway, we can work out the vector that this wall kind of is traveling along by thinking about the impulse, because the impulse is always perpendicular to the wall of impact. So the impulse is obviously just mv minus mu. So like this, they haven't even told us m, but of course it's not going to matter. We just get to this. This is just mv minus mu. So we want, so this is the vector that represents this impulse here. So we want that to dot with the vector that makes the wall, let's just call it AB, and make 0 because they're perpendicular. And of course we can just choose A to be 4 and B to be 3 here, and that's totally going to work. Minus 3 times 4 plus 4 times 3 is going to be 0. So we can just choose that to be the vector this wall is. And now anyone who's watched my previous Further Mechanics 1 videos knows what my method for doing these questions is. You call an angle here alpha, and of course alpha based on this vector is 4 across 3 up in a little triangle, so tan alpha is 3 over 4. Again, the 3, 4, 5 triangle comes out, and we get sine alpha is 3 over 5, and cos alpha is 4 over 5. The reason that's going to be super useful is because what I'm going to do to this is I'm going to rotate it by this angle alpha. I should have written alphas in here, but it doesn't really matter. And when you look at the formula book, it says anti-clockwise rotation, which is rotation this way. Is given by this matrix here. I'm going to rotate clockwise, and I know it's this vector here. If you are struggling to remember that, of course, what's the inverse of anti-clockwise rotation? Well, it's clockwise rotation. So to do clockwise rotation, it's just the inverse of this matrix. Swap those two over, it doesn't do anything. Make these minuses, puts the minus there, and then 1 over the determinant is cos squared minus sine squared, which is cos squared plus sine squared, which is 1. So the clockwise rotation matrix must be this. And of course, we can just apply that. Sine alpha, or theta, whatever angle you wanted to use, is 4/5, 3/5, -3/5, 4/5. I'm not even going to bother with the fifths. I'm just going to call it 4, 3, -3, 4, because the 1/5 is not going to matter, and I'll explain why in a second. But if you just rotate this vector by this matrix, that's going to rotate it down alpha degrees such that the situation is horizontal. We end up with this vector. Likewise, the matrix times the outward vector gives you this new vector, and this is great because now we can draw this picture like this. Maybe just double check that if you times this matrix by this vector here, it does rotate to something of the form k0. Check that on your own, but it definitely does, so therefore it's a horizontal vector, which is great. Also notice how this is 13, this is 13, so it's in 13 in, 13 out, which is fantastic. That's how it should be. It goes 16 down, and then it goes 9 up, but of course we know that this needs to be 16e, which is that 9 up, so therefore e is 9 over 16. And the fact that I just ignored the 1/5 is obviously not going to make a difference, because it just makes both these numbers a fifth of what they are now, and these numbers a fifth of what they are now, and then the 1/5 would cancel when you eventually come down to this. So we can, it's completely allowed that we're just lazy to and just don't do that. And that's the same for all of these matrix rotations. You can just take the factor out and ignore it, because even if you were doing it as you normally do, where you have to go back to one of these vectors, the inverse matrix would then, it would just be, if you would use the scale factor, the inverse matrix would take into account that, and if you didn't, then it wouldn't, and it would all be fine. So there's no problems there. So next, this thing also hits a horizontal wall because it's parallel to I. So now it hits a horizontal wall and comes out again. It's going in with speed 3 and 1, like so. So it goes out with speed 1 there, and then here should be 3e, but e is a third, so that's just 1. So this vector coming out is 1 minus 1, which means this angle is obviously 45 degrees because it's just an isosceles triangle. This angle here is tan inverse of 3 over 1, which is this here. So that's this angle there. And now so that's the 71 there. And now just to make sure we know what an angle of deflection is, if we imagine this particle going through the wall, the angle of deflection is the angle that you have to go from this to the new direction. So it's all of this angle here. And of course, by opposite angles, then this is 71 as well. And then just add those two things together and we get to the nearest degree, 117. The last question then, a good question. So we've got a lot to do here. All of this text is basically completely pointless. We'll be using this a lot at the end, although it's kind of obviously true, I guess. But we do need to just have that. You just need to keep this in mind because it is important. Aside from that, there's really nothing to really glean from any of those words there. So this there is just u sine alpha. This is u cos alpha. And now if we call this speed v here, coming backwards, now this angle here is just 90 minus alpha, right? Because this angle is 90, so this is 90 minus alpha. So coming backwards, we've got v cos of 90 minus alpha, and downwards v sine of 90 minus alpha. Now let's just stick with these for a second, because I don't really want to be using these. So let's use the compound angle formulas. So cos of 90 minus alpha is, cos is the one that goes cos, cos, minus sine, sine, but there's already a minus in here, so that goes plus. Cos of 90 and sine of 90 are super easy to evaluate, so that just becomes this. And then likewise, sine of 90 minus alpha, that's the one that goes sine, cos. And whatever sine is here, you keep that sine. And again, this just turns into this, which is nice. So those turn into these things. That's also just definitionally true based on how sine and cos interact, but whatever. So that just turns into those. Now let's call the speed coming out here w. This was stationary before, so it must just be flat coming out like w, like this. Now let's write down all the equations we can write down. So we have that this thing must equal this thing because the vertical components are preserved. So that's fine. We also have from the E formula going horizontally, we have E equals separation over approach. Separation is W plus V sine alpha because V sine alpha is going the other way. And approach is obviously just this U cos alpha. So that's there. And then momentum, we also do horizontally. So the mass times this one plus 0, I guess. I've also just tidied that up, I guess, just tidied it up like this. So this times m plus 0 times 3m is equal to this times m, but with a negative because it's going backwards, plus 3w, oh, sorry, 3m times w. So we get this here, which simplifies to that. And now they're asking us to specifically show this thing here. This is the speed of b. So this is w equals this thing here. Now you've got 3 equations to work with. The obvious thing about this is that it doesn't have any big v's in it. So we're going to have to get rid of those. The obvious way to get rid of big V is to use this equation here because it's very easy to write it in terms of u. It also doesn't have a sine alpha in it though, so we're going to have to try and get rid of sine alpha. And actually, the thing that really twigged this for me was this 1/4, because it's not obvious where you're going to get a quarter from because there are no 4s, right? So where are you going to get a quarter from here? Well, you could get a quarter if you added these equations together, because that would give you 4w, and then you could divide by 4 at the end, and you get a quarter. So that gave me the idea of adding stuff at some point. But likewise, we need to get rid of the v. So what I decided to do was put the v into here. I think it's into here first, actually. Obviously, you need to use the equation that has e in it. So we'll do that. So we're going to put the v into here. And then we're going to simplify a little bit for that. But then we can also put the v into here, which gets rid of it and gives you this. And now can you see what we're going to do here? I've already kind of given it away. But if we add these two things together, really nice, wasn't expecting it to be this nice. That thing will cancel with that thing. You get 4w as these two added together. Do some factorization, divide by 4, and you end up with what there was required. There's lots of ways that you could combine these things to make other things, and none of those are necessarily wrong. It's just about finding the specific thing that they want you to find. And again, keeping your eye on the prize, I say it all the time, to try and to help you get there by aiming for it because you know what it looks like. Super helpful. So seeing that 1/4 twigged it for me that at some point stuff was going to get added together so that I could then divide by 4 and get that out. Anyway, show that e is bigger than a third here. So again, we actually saw this in the 2023 exam, and I see it a lot in step mechanics papers. But one thing that's super common that's super helpful in these types of questions is making an equation that doesn't have any of the speeds in it, just has e and then some angle stuff. Because then usually you can say something about e if you just have angle stuff left over. So what I aimed to do here was use these three equations to just get rid, these are the same three equations we got before, obviously, to just get rid of v, u, and w. And the way to do that, I thought, was to rearrange this one for v, obviously, and then use this result for w, which is in terms of u only, and just throw this v into here and this w into there. And the reason that's really helpful is because now everything is a u, and we can just cancel out all of those u's because it's in every term, and there's nothing else. That all goes away. Divide everything by cos alpha at the same time, and you get this. And now this is just sine squared over cos squared, so that's tan squared. And then you can expand out this a little bit and rearrange, and you eventually end up here. And now tan squared is a positive thing. So therefore, e is 1/3 plus some positive thing. So therefore, e is bigger than a third. And that will be the answer to this bit here. And actually, what's really nice about doing this method for this question, although there are other ways to arrive at this, is that I've basically already done this question as well. I think I'm going to do 2 or 3 lines of working now in order to get 5 marks. Because obviously tan alpha is bigger than 0 because alpha is between 0 and 90. So I can just state that first. That's the first mark I got. And now for the other bound, I know that e is equal to this thing here, but e is less than or equal to 1. So therefore this thing is less than or equal to 1. And now we can just start solving. Times everything by 3, move that over, divide by 4, square root. And technically, I guess you could write tan is less than or equal to minus 1 over root 2, but you know tan alpha is bigger than 0 anyway, so that's the second bound anyway. So now we can bound tan between those two things. And that's all 5 marks got, and that's the entire paper done. Thank you so much for watching, and I'll see you next time.